US Physics Olympiad, year 2013, USAPHO, Semifinal exam. This exam consists of 6 problems, 4 problems A in the first day and 2 problems B section in the second day. For each day they were given 60 minutes. Problem A1. The flow of heat through a material can be described via the thermal conductivity K. If the two faces of a slab of material with the thermal conductivity K, area A, and the thickness D are held at a temperature differing by delta T, the thermal power P transferred through the slab is P equal Ka delta T over D. The heat exchanger is a device which transfers heat between a hot fluid and a cold fluid. They are common in industrial applications such as power plants and heating systems. The heat exchanger shown below consists of 2 rectangular tubes of length L, width W, and height H. The tubes are separated by a metal wall of thickness D and thermal conductivity K. Originally, hot fluid flows through the lower tube and speed V from right to left, and originally cold fluid flows through the upper tube in the opposite direction, left to right, at the same speed. The heat capacity per unit volume of both fluids is C. The hot fluid enters the heat exchanger at a higher temperature than the cold fluid. The difference between the temperatures of the entering fluids is delta Ti. When the fluids exit the heat exchanger, the difference has been reduced to delta Tf. It is possible for the exiting originally cold fluid to have a higher temperature than the exiting originally hot fluid, in which case delta Tf less than 0. Assume that the temperature in each pipe depends only on the lengthwise position, and consider transfer of heat only due to conduction to the metal and due to the bulk movement of fluid. Under the assumptions in this problem, while the temperature of each fluid varies along the length of exchanger, the temperature difference across the wall is the same everywhere. You need not prove this. Find delta Tf in terms of the other given parameters. Solution. Let's formulate the main idea how to solve this problem. We have 2 processes for heat transfers. One process is heat flows from hot liquid to cold liquid, and the other process is hot liquid is coming from one end, and during this motion we are getting hot liquid and we are losing cooler liquid. So we can count the rate how do we lose this heat. Let's convert it to equations. Because we suppose that temperature difference delta T is a constant along this pipe, we can write this equation for heat transfers for time delta T. That's a coefficient of conductivity multiplied by area, which is WL, divided by distance between layers, and multiplied by delta T, the temperature difference, and multiplied by time delta T. This is from one hand. From other hand, we have a hot fluid which is going from right end and this fluid is going cooler from left hand. And if we know what is temperature difference, we can count what was the heat transferred from this liquid, which is equal to this dq. In the same time, volume delta V of red fluid coming from a hot end, and this delta V equals this expression WH V delta T, and the same volume leaving this left end with a lower temperature. Suppose the temperature difference is a delta TR. It means that a red liquid getting heat dq equal this expression, and this dq must be equal to this dq, which is heat transfers for the same time delta T. Now suppose that a red liquid enters this pipe with the temperature TR, and the blue liquid enters this pipe with the temperature TB. It means that a red liquid leaves this pipe with temperature TB plus delta T, where delta T is a common temperature difference between red and blue liquids. So it means that overall temperature difference for a red liquid equal TR minus this expression, and the TR minus TB. That's our initial temperature difference between red liquid, which is going inside, and blue liquid, which is going inside. Now we can insert this TR to this expression for dq and equalize them. So from this equation we can find what is a delta T, which is a delta Ti over 1 plus alpha, where alpha is this coefficient. And now, because a red liquid exits with the temperature Tb plus delta T, and blue liquid exits with the temperature Tr minus delta T, we can count what is a total temperature difference for exiting liquids. So we have delta T final equal this 1 minus this one. So we have this expression, which is negative delta Ti plus 2 delta T, where delta T we already counted. So finally we got this answer where alpha is this coefficient, and we see that for very long pipe where L is very big, this coefficient is small, and total temperature difference could be negative. For alpha going to infinity for very long pipe, we can get a reverse result, which is interesting. US Physics Olympiad, year 2013, USAPHO, Semifinal exam. Problem A2. A solid round object of radius r can roll down an incline that makes an angle theta with the horizontal. Assume that the rotational inertia about an axis through the center of mass is given by formula I equal beta m r square. The coefficient of kinetic and static friction between the object and the incline is mu. The object moves from rest through a vertical distance h. Question A. If the angle of the incline is sufficiently large, then the object will slip and roll. If the angle of the incline is sufficiently small, then the object will roll without slipping. Determine the angle theta c that separates the two types of motion. Question B. Derive expressions for the linear acceleration of the object down the ramp in the case of I rolling without slipping and I2 rolling and slipping. Solution. First, let's draw the picture for this process. This is our free body diagram for this rolling. We have gravity force mg, we have force of friction F, and we have normal force N. Now let's assume that angle is small enough. It means that this motion is rolling without slipping. Let's write equation for this motion. For linear motion along this incline, we have this equation: ma equal mg sine theta minus force of friction. For rotational motion of this object, we have equation I alpha equal fr, where I equal beta mr square and alpha equal acceleration a over r, because this motion is without slipping. So we have these conditions. Now we put this I here and alpha here, and we will get that force of friction equal beta ma. And we can put this force in the first equation and find what is acceleration. So acceleration equal g sine theta over 1 plus beta, and now we can put this in equation for force of friction, and force of friction equal beta over 1 plus beta multiplied by mg sine theta. Now we have to check that this force cannot exceed mu multiplied by normal force. So mu mg cosine theta, that's maximum force of friction we can reach. From here we can find what is a critical angle. Tangent theta critical equal mu multiplied by 1 plus 1 over beta. For angles less than this angle, we have acceleration equal g sine theta over 1 plus beta. But for angles more than this one, we can just use a regular equation for force of friction, because if we have slipping, we have force of friction equal mu mg cosine theta, and after that acceleration equal g multiplied by sine theta minus mu cosine theta. That was the answer for question I2, and the answer for question I1 is acceleration, this one, g sine theta over 1 plus beta. So we just answer for all questions. US Physics Olympiad, year 2013, USAPHO. Semifinal exam. Problem A3. A beam of muons is maintained in a circular orbit by a uniform magnetic field. Neglect energy loss due to electromagnetic radiation. The mass of the muon is equal to 1.88 10 power negative 28 kilograms. Its charge is negative 1.602 10 power negative 19 coulomb, and its half-life is 1.523 microseconds. Questions. Question A. The speed of the muons is much less than the speed of light. It is found that half of the muons decay during each full orbit. What is the magnitude of the magnetic field? Question B. The experiment is repeated with the same magnetic field but the speed of the muons is increased. It is no longer much less than the speed of light. Does the fraction of muons which decay during each full orbit increase, decrease, or stay the same? The following facts about special relativity may be useful. First, the Lorentz factor for a particle moving at a speed v is gamma equal this expression. The Lorentz factor gives the magnitude of time dilation, that is, a clock moving at a speed v in a given reference frame runs slow by a factor gamma in that frame. The momentum of a particle is given by E as a vector equal gamma m v as a vector, where m does not depend on v. The Lorentz force law in the form dp over dt as a vector equal q multiplied by E electric field plus cross product of v and magnetic field B continues to hold. Solution. Question A. Let's count what is the force and what is the radius of orbit of this muons due to force from magnetic field. We have centripetal force mv square over r equal force from magnetic field, which is qvb. And also we can write the formula that the total distance to orbit equal to speed multiplied by period. Now we can put radius, which is vt over 2 pi, and put it in this formula. From here we can find what is the period. Period equal 2 pi m over qb, so it does not depend from velocity. And this period equal to half-life time, tau. So from here we can count what is a magnetic field in this case. Magnetic field equal 2 pi m over q tau. When we put numbers, we will get 4.84 millitesla. That's the answer for question A. In case of relativity, we can still use Lorentz formula for change of momentum, but momentum now equal gamma mv, and the radius still equal to vt over 2 pi. From this formula we can find that period equal previous period multiplied by gamma. But in a frame of reference of muons, which moves with a very high speed v, we have a time dilation with a factor gamma. It means that half period will increase on this factor, and again this time will be the period of rotation. So it means that this time will be half a period in a frame of reference of this muons. So it means that the answer for a question will not change. It means that half period will increase for the same factor, and we still have same fraction of muons decay during this period of rotation. US Physics Olympiad, year 2013. USAPHO Semifinal Exam. Problem A4. A graduated cylinder is partially filled with water. A rubber duck floats at the surface. Oil is poured into the graduated cylinder at a slow, constant rate, and the volume marks corresponding to the surface of the water and the surface of the oil are recorded as a function of time. Water has a density of 1 gram per milliliter. The density of air is neglectable, as are surface effects. Find the density of the oil. Solution. Let's draw additional lines on this graph. Initially, when we check these two lines with small circles and small crosses, they are connected in the beginning of time. It means that oil was absent at the 0 point. And in this point, the total water level was V1 equal 243 millimeters. It means that it was total volume of water plus volume displaced by this rubber duck. And after that, we start to fill oil. And in point 6, we see that the rate of this filling was constant. It means that in this point, our duck start to completely float in oil. Now we exclude the possibility that duck floats between water and oil, completely submerged on the oil level. So it means that after 0.6 minutes we have water level is constant, 100 milliliters. And we can subtract from V1 VW. That will be VDW, the volume of water displaced by a rubber duck, which is 143 millimeters. This is how this duck completely floats in water. Now let's check a red line. The slope of a red line showing in the end after 6 minutes how fast is this oil filling this cylinder. And it means that if we continue this line to the beginning, we can find what is the total volume of oil in our container. That will be this amount on the right end of this red line minus this point on the left end of this red line. Let's count it. So we have VO, that's amount of oil in the end of the process, which is 142 millimeters. And if we check this graph now, we can say that this is the level of oil, 385 millimeters. The level of water is 100, and the distance between green line and blue line, that's volume displaced by our duck from the oil. If we count it, we can count this amount. So we see that VDO, that's the volume displaced by a rubber duck from oil, which is 187 millimeters. If we compare these two volumes, this is the volume displaced by duck from water, and this is volume displaced by duck from oil. And now we can find what is rho of oil. So we have this equation: displaced volume of oil multiplied by rho of oil equal to displaced volume of water multiplied by rho water. And now we can find what is raw oil. That will be 0.77 gram per milliliter. That's the answer for problem A4. Only thing that we don't know yet if this rubber duck is floating in the oil or it's completely submerged and floating between water and oil border. US Physics Olympiad, year 2013, USA PHO, semifinal exam, problem B1. Shown below is the Blackbird, a vehicle built in 2009. There is no source of stored energy such as a battery or gasoline engine. All of the power used to move the car comes from the wind. The only important mechanism in the car is a gearbox that can transfer power between the wheels and the propeller. The Blackbird was driven both directly downwind and directly upwind, as shown below. In each case, the car remained exactly parallel or anti-parallel to the wind without turning. The tests were conducted on level ground, in steady uniform wind, and continued long enough to reach the steady state. When driving downwind, the builders claimed that they were able to drive faster than the wind, that is, with a speed v greater than speed of wind, so that the car experienced relative headwind while traveling. Commenters on the internet claimed often angrily that this was physically impossible and that the Blackbird was a hoax. Some commenters also claimed that the upward case was physically impossible. Question A. Consider first the downwind faster than the wind case. Is the motion actually possible as claimed? If not, offer a brief explanation. If the motion is possible, is power transferred from the propeller to the wheels or vice versa? If the motion is possible, what ground speed is attained? For this question, suppose that when transferring power in either direction between the propeller and the wheels, a fraction alpha of the useful work is lost. Let the wind speed be Vw. Neglect all other losses of energy. Question B. Answer the previous question for the upwind case. Solution. Both modes are possible as claimed. The solution uses the idea of a center of mass power, which we will review below for interested readers. The solution itself starts on the next page. For simplicity, we will work in one dimension. If a particle moves with a speed v1 and experiences the force F, then the rate of change of its kinetic energy is P1 equal F multiplied by V1. Suppose this force is exerted by an interaction with the second particle, which moves with the speed V0. The rate of change of its kinetic energy is P2 equal negative F V2 by Newton's third law, and the total is P equal P1 plus P2, which is equal F V1 minus F V2, which is equal F VR, where VR is the relative velocity. If we move into a different reference frame, Both P1 and P2 change, but P stays the same, as all frames agree on the relative velocity. This is straightforward, but it becomes more subtle when applied to a system more complicated than a particle. The speed v becomes the speed of the point of application of the force, while the power p must be generalized to include internal energy. We will write the energy of a system as E equal E center of mass plus E internal, where the center of mass energy E center of mass equal m v center of mass square over 2 is the kinetic energy associated with the motion of the center of mass, and E internal accounts for everything else, such as the rotational energy of the wheel or propeller. As an example, consider an accelerating bicycle. The force that pushes the bicycle forward is the friction force with the ground. However, if the wheels are rolling without slipping, then at every moment the relative velocity between the ground and the part of the wheel touching the ground is exactly zero. Thus the power is zero, so E is constant. This is because the increase of E center of mass is compensated by a decrease in the chemical energy of the cyclist, accounted for in E internal. Thus, energy arguments appear to tell us nothing useful about the motion of the bicycle. Similarly, energy arguments tell us nothing definite about the blackbird's wheels or propellers. It is more useful here to use center of mass power. This concept is not covered in most textbooks, but interested readers can consult section 13.5 of Holiday Resnick and Crane 5th edition. The idea behind the center of mass power is that the center of mass of system satisfies F equal ma center of mass, where F is the total force on the system. This is essentially the same equation as we would have for a single particle of mass m, so by the same proof of the work kinetic energy theory for particles, P center of mass equal force multiplied by V center of mass, P center of mass equal dE center of mass over dt. The center of mass power P center of mass only contributes to the center of mass energy. Crucially, it only depends on the velocity of the center of mass, not on any other details of the system. Now consider two systems interacting by a force F whose centers of mass move at a relative velocity Vr. By the same argument as above, the net center of mass power is P center of mass equal V multiplied by Vr. By conservation of energy, this change in center of mass energy must be compensated by an opposite change in the internal energy. Now we turn to the analysis of the downwind case. We take all velocities to be positive. In the steady state, the velocity of the blackbirds is constant, so the force F on the propeller is balanced by a force negative F on the wheels. For the system of the propellers and higher, we have P center of mass equal F multiplied by V minus V W. By energy conservation, the internal energy of the propellers and air must change at the rate P propeller equal F multiplied by VW minus V. Since we have assumed no extraneous energy losses, the internal energy of the air doesn't increase at all. So this is just the change in the internal energy of the propeller. By similar reasoning, the internal energy of the wheels and the ground must change at the rate P wheel equal F multiplied by V. And again, since there are no extraneous energy losses, this is the rate of change of the internal energy of the wheels. Now we determine the sign of F. If the blackbird moves downwind faster than the wind, V greater than VW, then P wheel and the P propeller have opposite signs, with the P wheel greater than P propeller in absolute value. Thus, the force F should be positive in the direction of the wind, so that P wheel is positive and the P propeller is negative. That is, power is transferred from the wheels to the propeller. In general, power should always be produced by the force with a larger relative velocity. In the steady state, the total internal energy of the blackbird is constant, so absolute value of P propeller equal to 1 minus alpha multiplied by P wheel. So V equal to VW over alpha. With a sufficiently low energy loss, any speed is possible. The argument here is somewhat counterintuitive. A tempting but incorrect counter-argument is that since the internal energy of the blackbird ultimately comes from a decrease in the center of mass energy of the air, which is slowed down by the propeller, the internal energy must always be supplied by the propeller. One way to see this argument doesn't work is to note that in the reference frame where the air is still and the ground is moving, the same argument would suggest that internal energy must always be supplied by the wheels. The point is that changes of center of mass energy are completely different in different reference frames, as mentioned above. They cannot be used to determine the direction of flow of internal energy, which does not depend on the reference frame. In all frames, the force of the wind slows the rotation of the propeller, and hence power must be transferred from the wheels to the propeller. We now consider the upwind case. We'll keep all the sign conventions the same, except we'll take V be the leftward speed of the blackbird, then absolute value for P propeller equal F multiplied by V plus VW, and P wheel equal negative FV. Since absolute value P propeller greater than absolute value for P wheel, power is transferred from the propeller to the wheels, and we again have F greater than 0. It means that in both cases the force on the propeller is in the direction of the wind as expected. The energy balance equation is absolute value for P wheel equal 1 minus alpha multiplied by P propeller. So from here V equal VW 1 over alpha minus 1. Again with a significantly low energy loss, any speed is possible. US Physics Olympiad, year 2013, USA PHO, semifinal exam. Problem B2. This problem concerns three situations involving the transfer of energy into a region of space by electromagnetic fields. In the first case, that energy is stored in the kinetic energy of the charged object. In the second and the third cases, the energy is stored in the electric or magnetic field. In general, whenever an electric and the magnetic field are at an angle to each other, energy is transferred. For example, this principle is the reason electromagnetic radiation transfers energy. The power transferred per unit area is given by the Poynting vector S equal 1 over mu0 multiplied by a cross product of electric and magnetic fields. In each part of this problem, the last subpart asks you to verify that the rate of energy transfer agrees with the formula for the Poynting vector. Therefore, you should not use the formula for the Poynting vector before the last subpart. Part A. A long insulating cylindrical rod has radius r and carries a uniform volume charge density ρ. A uniform external electric field E exists in the direction of its axis. The rod moves in the direction of this axis at a speed v. Question I. What is the power per unit length P delivered to the rod? Question 2. What is the magnetic field B at the surface of the rod? Draw the direction on a diagram. Question 3. Compute the Poynting vector, draw its direction on a diagram and verify that it agrees with the rate of energy transfer. Part B. A parallel plate capacitor consists of two discs of radius r separated by a distance d much less than r. The capacitor carries a charge q and is being charged by a small constant current I. First question. What is the power P delivered to the capacitor? Question 2. What is the magnetic field B just inside the edge of the capacitor? Draw the direction on a diagram. Ignore fringing effects in the electric field for this calculation. Question 3. Compute the Poynting vector, draw its direction on the diagram and verify that it agrees with the rate of energy transfer. Part C. A long solenoid of radius r has n turns of wire per unit length. The solenoid carries a current I, and this current is increased at a small constant rate dr over dt. First question. What is the power per unit length P delivered to the solenoid? Question 2. What is the electric field E just inside the surface of the solenoid? Draw its direction on a diagram. Question 3. Compute the Poynting vector, draw its direction on a diagram and verify that it agrees with the rate of energy transfer. Solution. Part A. A long insulating cylindrical rod has a radius r and carries a uniform volume charge density ρ. A uniform external electric field E exists in the direction of its axis. The rod moves in the direction of its axis at speed v. Let's imagine that our rod oriented perpendicular to the board and moving inside the board, and the electric field has a direction inside the board. So it means that we can count what is the power delivered to the unit length of this rod. Let's take a cylinder from this rod with length L, and total charge of this cylinder will be Q equal rho pi r square L, and total force from electric field on this cylinder will be QE, which is rho pi r square LE, and the total power delivered to this cylinder will be FV, which is rho pi r square LEV, and the total power delivered per unit length of this rod is rho pi r square EV. That's the answer for question 1. Question 2. What is the magnetic field B at the surface of the rod? Here we can use Ampere law and make an integral right near the surface of this rod. The total current through the surface of this rod will be rho pi r square V. And now we can count what is a magnetic field produced by this current. We have this equation: 2 pi rb equal mu0 rho pi r square V, and the magnetic field equal 1/2 mu0 rho rv. That's the answer for question B. And also we can mention that if current is going inside the board, the direction of this magnetic field will be clockwise. Question 3. Compute the Poynting vector, draw its direction on a diagram, and verify that it agrees with the rate of energy transfer. Because electric and the magnetic field perpendicular to each other, we have this formula for Poynting vector, and that's equal to 1/2 rho rve. And the direction for this vector is due to cross product of our electric and magnetic field will be inside of this wire. Poynting vector giving us power delivered per unit area, and we just counted the power delivered from electric field to unit length. So we need to divide this power by 2 pi r to get expression for power delivered to unit area. So if we take this P and divide this by 2 pi r, we will get 1/2 rho rve, which is exactly equal to computed Poynting vector. So that's the answer for question 3. Part B. A parallel plate capacitor consists of two discs of radius r separated by distance d much less than r. The capacitor carries charge Q and is being charged by a small constant current I. First question. What is the power P delivered to the capacitor? Question 2. What is the magnetic field B just inside the edge of the capacitor? Draw the direction on a diagram. Ignore fringing effects in the electric field for the calculation. Question 3. Compute the Poynting vector, draw its direction on a diagram, and verify that it agrees with the rate of energy transfer. First, we have to count what is the capacitance of this capacitor. That will be epsilon 0 multiplied by area, which is pi r square, and divided by distance between plates. And now we can count power. Power equal current multiplied by voltage, and voltage equal total charge Q divided by capacitance. And capacitance we already counted. And finally we have expression for power, which is answer for question I. First we can count what is electric field between capacitors plates. That will be surface area density sigma over epsilon 0, which is equal to this expression. Now we can count what is the total flux of electric field through this area of capacitor. That will be Q over epsilon 0. And now we can use Ampere law to count what is a magnetic field produced by current filling this capacitor. Because we don't have any current between plates, we have only changing electric field. We can surround this capacitor by our Ampere loop and count the integral along this loop. According to Ampere law, this integral must be equal to this expression, mu0 epsilon 0 multiplied by rate of change of electric field flux, which will give us this equation. And now we can count what is a magnetic field right around this capacitor. That will be mu0I over 2 pi r. Again, if capacitor oriented such way that positive plate is looking to us and the negative is outside, so it means that current is going inside the board and the magnetic field is going around the capacitor clockwise. That's the answer for question 2. Again, we have electric field and magnetic field are perpendicular to each other, and the pointing vector looking inside the capacitor. Finally, we have pointing vector equal this expression, which is this expression. Last step is to multiply pointing vector by area of side of this capacitor. Finally, when we will multiply pointing vector by side area of this capacitor, which is 2 pi rd, we will get total power delivered to this capacitor, which is exactly equal to power delivered to this capacitor using previous questions. So that's the answer for question 3. Part C. A long solenoid of radius r has n turns of y per unit length. The solenoid carries a current I, and this current is increased at a small constant rate di over dt. First question. What is the power per unit length P delivered to the solenoid? Question 2. What is the electric field E just inside the surface of the solenoid? Draw its direction on a diagram. Question 3. Compute the pointing vector, draw its direction on a diagram, and verify that it agrees with the rate of energy transfer. First, let's answer for question 1. What is the power per unit length P delivered to solenoid? First, inductance of a solenoid equal to this expression, mu0 n square pi r square L. Next one is voltage. Voltage equal inductance multiplied by di over dt, which is this expression. And finally we can find what is delivered power. That will be current multiplied by voltage. That's this expression. And this is the answer for first question in this section. Question 2. What is the electric field just inside the surface of the solenoid? First, we can tell what is the magnetic field inside of the solenoid. That's equal mu0 and I. And now we can use Ampere law to find what is electric field just around a solenoid inside the surface, because we know what is the rate of change of magnetic flux through this surface inside the solenoid. If we do Ampere loop just below this surface of solenoid, inside of it, and do integral, this electric field due to symmetry is constant and going around, and that's equal to a rate of change of flux of magnetic field, dFB over dt. And now we can rewrite this formula, because integral equal 2 pi r multiplied by electric field, and dFB over dt equal this expression. Finally, we have electric field equal 1/2 mu0 and r di over dt, which is answer for question E. And we can find the direction of this electric field. Suppose that current is going clockwise, if solenoid going inside of this board, and change of electric current again going clockwise. It means that flux is increasing, and EMF produced in this solenoid must produce current, which is decreasing change of flux. So it means that electric field must go counterclockwise, just below the surface of this solenoid. That's the direction of electric field. Question 3. Let's do this. We just need to use formula for pointing vector. Because again magnetic field and electric field perpendicular to each other, we have this formula, and we can put expressions for electric field and magnetic field in this formula. That will be this one, and finally that will be this expression. That's the answer for question 3. And now we can find what is the direction of this pointing vector, because here we have cross product electric field multiplied by B. We have electric field going counterclockwise and magnetic field going inside the board. It means that the direction for pointing vector is going inside the solenoid. And last step to compare this result to result in first question with delivered power, we need to multiply pointing vector by side area of this solenoid, which is 2 pi r multiplied by L, which is S multiplied by 2 pi r multiplied by L. And finally that's equal to this expression for power using pointing vector, and this power exactly equal to power in the first question. So that was the answer for question 3.